Good evening, ladies and gentlemen. In this video, I am going to use EViews software for basic estimation of time series model. My dear colleagues, follow me on my YouTube channel. Kindly subscribe to it and click on the bell icon so that you could get notification about my other videos. Also visit my Facebook page. Here is the web link, and you can find many different videos and other things. Let me start with the data and the work file documentation. In this video, I'm going to use monthly data, which is available from January 1960 to December 2011, and the data is on 4 variables: M1, which stands for money supply, and that is measured in billions of US dollars. The second variable is IP, that is industrial production, and that is measured in index levels. The third variable is T-bill, that is 3-month US Treasury rate, and the final variable is consumer price index level. Suppose we want to use simple time series regression, and our aim is to estimate a model which captures movements in money supply based on industrial production, consumer price index, and treasury bill. As a first step, it may help to open these variables as a group and plot the series in order to observe trends in the data. And if you look at this graph, money supply seems to grow over time. So adding a time trend may improve the fit of the model because there is a positive trend in money supply. Similarly, consumer price index and industrial production also seem to move together with M1 and also grow over time. However, the treasury bill variable appears to have a different pattern from money supply and CPI and industrial production. We can specify a time series equation in EViews, which is very easy, and we follow some basic steps that we introduced in the basic estimation tutorial. And I'll start with the example number 1, and I have data in this file, data WF1, that is the work file, and I can use this procedure in the main menu. I will select object, then I will go to new and object and equation, and I will click OK, and then the equation estimation box will open, and I can specify various variables like this. Now if you look at this variable, at this equation estimation box, there are 4 variables that I have used here, and I'm going to estimate the natural log of money supply on constant, and log of industrial production, and log of consumer price index, and treasury bill, and the method is least square, and here is the sample, that is from month 1 1960, that is January 60 to December 2011. Now the estimation output is shown here. If you look at this box, a number of things stand out. All the variables appear to be highly statistically significant based on these p-values. Now in this regression of log of M1 and log of industrial production, log of CPI and treasury bill, all the variables seem to be highly statistically significant. The R squared value is also very high, that is 0.99, and it results in implication that 99.2% of the variation in the dependent variable is explained by these three variables, that is log of industrial production, log of consumer price index, and treasury bill. Normally, this would imply a very good fit of the model. However, we must be very careful against these results. High R squared does not necessarily mean that the model is a good fit. Why? Let us take a look at the behavior of the residual in this equation view. I am following this procedure that I have opened equation number 1 that I just showed to you, and then I clicked on view in the EViews on the equation box, and then I selected actual fitted residual, and then I got this graph. So these two are the actual and the fitted values of the residual, and these are the residuals. So the residuals of this regression appear to have long periods of positive values followed by long periods of negative values, and this provides a very strong evidence about serial correlation. So this means that this model suffers from a serial correlation. The error terms are serially correlated. We may also use distributed lag models, which are easy to use and to specify in EViews. In these models, one or more variable affects the dependent variable with a lag. Lags of dependent or independent variables can be specified directly in the equation box in EViews. For example, we want to estimate how M1 is affected by CPI and its first two legs in log form. Then we will type this command, that is ls log M1 constant log CPI log CPI into -1, this is first leg, log CPI -2, this is second leg, and then we will enter this model and we will get the following results. So we will get these results. Now if we notice, we have now 622 observations in this estimated model, because we are using two legs of CPI. The R squared and the F statistics value are very high, and that is surprising, especially since some coefficients do not appear to be very significant. For example, the coefficient for the log CPI is not significant, and the coefficient for the log the first leg is also not significant at 5% level. So what causes these results? It turns out that there is a substantial correlation between CPI with first leg and CPI with the two legs. So we can look at the correlation matrix of CPI and its first two legs. To create the correlation matrix, we follow these steps, and we say show CPI into -1 and CPI into -2, and then we follow these steps, and finally we get this correlation matrix. And if you look at these series are highly correlated. You see 0.99, 0.99, 0.99. So the correlation is very high among these series. So we can see from the autocorrelation, from the correlation matrix, the series are highly correlated. So there is the issue of multicollinearity. This multicollinearity makes it difficult to estimate the effect of each leg. We can also look at the coefficient variance decomposition from the view menu of equation box, and it's this. And here there are various information regarding the eigenvalues, the condition numbers, variance decomposition proportions, and the eigenvectors. The top portion shows the eigenvalues, which are sorted from the smallest to the largest. In our case, the condition numbers are much smaller than 1 divided by 900, that is 0.001, which indicates the problem of collinearity. The middle panel displays the variance decomposition proportions, the proportion associated with the smallest condition number. As you can see, 3 of the values are above 0.50, which indicates that there is a high degree of collinearity between these three series, CPI1, CPI minus 1, CPI minus 2. You can just as easily specify a model containing a large number of legs without having to explicitly type out all the legs by this command, that is mi m1 c cpi 02 minus 12. So there are 12 legs, and there is also CPI at the level. So we can also do this, and if you follow this, here are the results. These are the various coefficients of the legged values of the CPI, and this is the coefficient of the CPI. So again, taken individually, none of the coefficients except leg 12 is statistically significant. However, the R squared value and the F statistics are very high. Similar to previous example, the issue here is that there is high degree of collinearity among all regressors. A way to deal with the high collinearity is to fit a polynomial distributed leg model. Here is another example, and here I am going to regress log of m1 on constant, log of m1 with first leg, and then log CPI and log CPI with first and second leg, and if I do that, the results are here. Now if we can look at these, we will notice that the leg dependent variable of log m1 is close to unity and is highly significant. If errors are serially correlated, OLS estimates are biased and inconsistent in the presence of leg dependent variables. Ladies and gentlemen, this is a very brief presentation about time series model estimation in EViews, and further detail will be given in the coming videos. Kindly subscribe to the channel and click on the bell.